Hello my people, I hope we're doing well today. These are the videos on Newton's method, which is the second approximation method that we're going to be studying. And since it is another approximation method, I thought it was a good idea that we should review the first one that we did, which was linear approximation. Okay, I think that was section 3.10, so the last section in chapter 3. Remember that the principle was, if you were looking for, let's say, the square root of 95, you could use the square root of 100 to estimate it based upon the fact that you could find a tangent line to the curve of y is equal to the square root of x, and that tangent line would give you a tangent line that lay sufficiently close to the curve, and therefore an evaluation of the output of 95 at the tangent line would give you an approximation for the evaluation of an output of the original function. So, and if you're like, what? I don't remember that. Well, let's go ahead and do an example and run through it. So, but even without the function in our mind, we can think of the fact that square root of 95 is sufficiently close to the square root of 100, and we're going to use that, okay? But since we're taking the square root, really, this value right there is an output value for that function. Y is equal to the square root of x. But since we're going to be taking the derivative, let's go ahead and put it into its fractional exponent form. And if we do, y prime is equal to 1/2 x to the negative 1/2, or if I want to simplify this into that just because I can, okay? Now, that gives me the slope of any point on that original function. And if I want to find the tangent line at x is equal to 100, now I know that x is equal to 100 implies the ordered pair 110 because, you know, the square root of 100 is 10, and that's the whole reason why we're using that as the value. Because if I can find one that is easy to do, that is sufficiently close, meaning nearby, then I can use the tangent line from that point to estimate my given value. Now, in order to find the equation of a tangent line, I need two things. I need point and I need slope. Well, I have point. Let's go ahead and find the slope at that particular value. And I just need to evaluate y prime at 100. And that gives me 1 over 2 times the square root of 100, or 1 over 20. That means that I have an equation of a tangent line that is y minus y1 is equal to m times x minus x1. And that is going to give me, if I want to turn it into slope-intercept at this point, when I simplify, 1/20 x plus 5. Now, I'm going to give you a sneak peek from the other one. Basically, the idea is from the next page. The idea is that since this is the curve and this is the tangent line, out here at 95, let me go ahead and use a different color for this. Right here, notice that they look indistinguishable. That's kind of the point, right? So what I want to do is I want to evaluate this tangent line right here, right? This is the equation of the tangent line. And if I evaluate that bad boy at 95, what I'm going to get is 95 over 20 reduces to basically 19 over 4. Okay, it has to, you know, because they both have 5 as a factor. 19/4 is 4 3/4, or 4.75, plus 5 gives you 9.75. And that is the approximation that I get because they lie so close together, because I chose a point that was, like I said, sufficiently close. Now, I see the fact that here the true approximation is 9.747, pretty close, and if I actually want to evaluate the percent error, I can do that, okay? So you get the approximation minus the actual over the actual times 100, and that'll give you a percentage point, and it is an error of 0.033%. Pretty darn good. And like I said, Basically, the whole point is you want to find a point that is sufficiently close based upon the curvature of whatever function is that you're using, so that a tangent line looks almost indistinguishable. And I've even zoomed in a bit here, and you can see the fact that it truly is indistinguishable from it. Okay, now we're going to use something, we're going to use tangent lines and a logic that is similar to this on our next approximation method, and this is properly what is called Newton's method. We're going to use it to approximate zeros. Okay, so let's say that I'm given the question 1/3 x cubed plus 1/2 x squared plus 3 is equal to 0, meaning for what value of x is this cubic 0? Well, if I kind of think about that, as if I back up a step, I know that that is the question that you ask yourself when you're asked for the zeros or the x-intercepts or the solutions for this cubic function. And if I look at the graph, I see this cubic function has a 0 right over here, pretty close to -3. I'm going to go ahead and use that, and we're going to basically use the tangent line at -3 in order to approximate a 0. Because if you come down here and you sort of ish a tangent line from here, right? What's going to happen here is the 0 of the tangent line is going to wind up being an approximation for the 0 of the function. And that's kind of how we're going to move forward. So, since we're finding the equation of a tangent line, let's go ahead and find f prime, since I know we're going to need the slope at some point. And when I differentiate that first term, the 3 that gets pulled down cancels with the 1/3, I get an x squared. The second term, the 2 that gets pulled down cancels with the 1/2, I just get an x, and of course the derivative of that constant term is equal to 0. Now remember, if I'm finding the equation of a line, I need two things, point and slope. Well, let's go ahead and find the point and the slope. I am using the tangent line at x is equal to -3, and we're looking for the tangent line to the curve, so the point that we're looking for needs to be on the curve. And so if I have -3, all I need now is the y-coordinate. And that means that I'm just going to plug in to find the corresponding y-coordinate. -3 cubed, -27 times 1/3 is -9. -3 squared is +9 times 1/2 is 9/2 plus, that's 3, plus 3, and that's going to give me -3/2. That means that I have my point. My point that I'm going to use, my x1, y1, is -3, -3/2. Now I need my slope, which means I'm going to evaluate f prime at -3, and that's -3 squared plus a -3, that's 9 minus 3, or 6. So basically, I have my x1, y1, and my m. I get y minus y1 is equal to m times x minus x1, and that's going to give me y plus 3/2 is equal to 6x plus 3, and when I put it into slope-intercept form, I'm going to get 6x plus 33/2. That is the tangent line to the curve. Now let's go ahead and I'm going to show you what that looks like, okay? And basically what happens is that tangent line, like I just sort of ished, but here is a, Desmos, or I forget which grapher program I used. This is a computer-generated one, and you see how close those zeros are. In fact, I zoomed in, and you see exactly how close those are, right? But you need to actually find the 0, okay? And the tangent line, if you actually solve for the 0, you set 6x plus 33/2 is equal to 0 and solve for x, you get -0.275. Now, that's not bad, right? If we chose a 0 that was sufficient, we chose a value of x that was sufficiently close to the 0, and the equation of our tangent line brought us even closer to the new 0. So, how do we get an even better approximation? Well, the answer is we do another tangent line at that new approximation, okay? So if we choose a 0 approximation sufficiently close to the real 0, the method will yield a pretty good approximation. So we're going to do another one. So we basically use the 0 from the tangent line to get another estimate and another tangent line, which will give us another 0 approximation, which we can then do another tangent line at that new approximation, and over and over and over and over and over again. Okay? So unlike linear approximation, this winds up being an iterative process. But let's go ahead and find the point. We know that f of negative 2.75, and you can basically, 1/3 and negative 11 fourths cubed plus 1/2 and negative 11 fourths squared plus 3, and that's going to give you negative 29 over 192, and even I'll appreciate the fact that a decimal approximation is probably a little bit easier at this point, and the decimal approximation you get is negative 0.151. Okay, so your point, right, is negative 2.75, negative 0.151. Now let's find the slope. So we have f prime of negative 2.75, or negative 11 fourths, and that's going to be negative 11 fourths squared plus negative 11 fourths, and that's going to be 121 over 16 minus 11 fourths, or minus 44 sixteenths, which gives us 77 sixteenths. So my slope is 77 sixteenths, so that's my m. So if I go ahead and y minus y1, 29 over 192, is equal to 77 over 16x plus 11 fourths. You can use that to approximate, and basically that winds up being, in terms of approximating both your m value and this y1 value over here, 4.813x plus 13.083. Now, if you were actually going to use that version, you would want the exact values for those two numbers stored into your calculator, okay? But let's go ahead and we can find the 0. If we look, basically, if we set either this or this, and basically plug in a 0 for y and solve for x, what we're going to get is x is equal to negative 628 over 231. Yeah, how's that for a common denominator? Which gives you approximately negative 0.2719. And you're thinking to yourself, my gosh, this is a torturous process. And I could do it again and again and again and again. But actually it winds up being easier just to use a formula. Now, I know that that is really, really contrary to what I usually tell you, but this is one of those formulas that is going to save you a lot of time, is easy to memorize, and therefore it sort of fits into our, we're going to use it often enough, meaning in this section, we're going to use it all the time because it's the entire point of this section. We're going to use it often enough and it's easy enough to memorize, so we memorize. So we need to remember that the general form of the tangent line is y minus y1, or in this case, the f of x sub 1, and the slope is f prime of x sub 1, and this is x minus x sub 1. Now, if we're looking for the 0 of the tangent line, we simply need to plug in 0 for the y, and then we need to solve for this x sub 2, right? Because that's the value that I'm looking for. That x turns into x sub 2 because I know that that x is what I'm solving for, and it becomes the next value. So if we actually just, solve for x sub 2, and you guys should know how to do this, z problems and all sorts of fun stuff like that. And we could do the, so once we find x sub 2, we know that x sub 2 is equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. And we could do the same thing for x sub 3 and beyond. So really what we get here is we get a formula for the general next term. So remember, x sub n plus 1 is the next 0, and this is the formula that you need to memorize, okay? Like I said, it's a formula that fits our two criteria for worth memorizing. It's easy to memorize, and you will use it a lot. So what we're going to do is this is a very calculator dependent one because it's formula based, and let's go ahead and let's work through what we're going to do here. Now, let's go ahead. Let me go ahead and turn that off. No, actually, I'll tell you what. We're just going to move it up here, and now turn it off. Okay. Haha, there we go. Okay, so what we're going to do is we're going to go into our y equals, and we're going to say, okay, well, I know that this is going to be the square root of x. Now, you can either, in this second one, put the actual derivative, or if you're a little bit lazy, and this is not a bad lazy, you can go ahead and do the derivative. That's alpha f2 in order to get that pop-up menu. And you can ask for the derivative with respect to x of your y1 where x is equal to x. And that will automatically generate the derivative in y2. Now, let's go ahead and let's turn off the derivative, and let's make sure, oh, actually, we're not doing square root of x anymore. We're doing the cubic, right? So sorry about that. So 1/3 x to the third, and then it's what is it? Is it minus 1/2 x squared? Give me a second. It's plus 1/2 x squared. Okay. Oh. Nice. So plus 1/2 x squared plus 3. Okay. Now let's go ahead and let's go to the window and let's set -5. Sorry, it's -5 to 1. The x scale of 1, and then the y scale, let's do, I don't know, -5 to 5. And let's graph it just to make sure that what we see on the screen is what we saw earlier. And it is, right? We see the fact that we have a 0 roughly at -3. And what we're going to do in terms of putting that into doing this on the main screen is we're going to take our first estimate and we're going to go -3, enter. Here's the reason why we're going to do that. This formula right here, okay, we're going to be using the fact that x sub n and x sub n and x sub n are all equal, right? That is the previous estimate, and isn't that what -3 is? That means that I can set up the formula as answer minus y1 of the answer, because that would be your f of x sub 1, right? Because f of x was plugged into y1, over y2 of your answer, and then I'm just going to press enter, and that's going to give me my next approximation. Here's the fun thing. Not only is that going to give me my next approximation, and again, and again, and I really just have to start pressing enter, 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 until such time as the numbers stop changing, and the numbers stop changing right about there, okay? Now, I will give you a chart to fill in, so I do want you to keep track of those, okay? So the way that looks, at least for right now, is something like this. So basically, this is sort of the chart version, and you would fill it out, and your 0 to 3 decimal places, and I haven't decided whether I want you to give me the whole thing in terms of all the decimal places or the usual 3 decimal places, but the instructions will be explicit, okay? And that winds up being your approximation, okay? Now, that brings us to the end of the first video. That lays out sort of how it's similar to linear approximation, running through the actual legwork of finding all of those equations at the tangent line, and then of course finding and deriving the formula for you and showing you how it works. In the next video, of course, we will just run through a bunch of examples. So, bye.